Something or there's that is right. अच्छा समझ में नहीं आ रही है from how what I get from and then side will have like West Bengal, here Assam, police Assam, Assam also people are candidates for Assam particular. I'm not side with that. That is for some people from Gujarat and they will be here for the conference also. Yesterday I learned some. You can't tell me what are the other things you want. So that accordingly I will tell. I will not have any overlap. That what other things you have learned? Here, this question. Permanent. Permanent. Permanent is the other benefit we want to write. Determinant is like alternative, but depending on the other we can take other that human and it by a finite grid. So it can have a finite graph and some approximated graph. So whatever grid points you are having inside, then you can find grid like in our school days, we measure the area. Did you measure the area of by doing this thing? If it is more than half, count one. If it is greater than half, do not count. That kind of thing we did. How do you find the area of this whole thing? Now put it on the graph paper. How many units, square units it completely covers, that is count. And whatever it covers more than half, count that one. Whatever it covers less than half, do not. That gives you an approximation, right? In a similar way, at the or otherwise talk about your integration area and R2. That's what you do. So when you take finer and finer grids, so you will have a graph, approximated grid graph for this set. And that grid graph will be approximate. Right? The shape of that. So then essentially like the question would be like, can you have two non-isomorphic graphs within the same spectrum? So in that case, some that you will listen in the same, but then they are because the graphs are. So ultimately, those things came that graphs, co-spectral graphs, those things are there. It is like you read that survey article, they will tell. Okay. I have 30 minutes. Okay, so I was talking about this. Now, if I construct this vector, will this vector be the Laplacian eigenvector? Will this satisfy? Now, so for example, at this vertex or at x2, what is the corresponding Laplacian eigenequation? The eigenequation will be 2 times x2 minus x1 minus x3 should be equal to lambda 2 times it. Right? Because it was for the path. That was the case. Now also this is the case. That is not a problem. What about this one? Now earlier it was xn minus xn minus 1 was equal to lambda 2 times xn. Because earlier everything was 1. Right? But now it has changed. So now it has become 2xn. And I have done this. I have added an h here now. That is why the dB has become 2. So I have put 2 minus xn also. So I will write minus xn minus 1 minus xn is equal to lambda 2 xn. That also satisfies. Okay. And here inside also it will satisfy. Here also it will satisfy. Here also it will satisfy. So what does that mean? That means whatever was an eigenvalue with a corresponding eigenvector x, I have x are written in the symmetric way. Symmetric way would mean this way. x1, xn, and again xn to x1. That is now an eigenvector for the bigger bracket. For the same eigenvalue. Okay. What about the rotation? And the rotation will always be that. Because this is a cycle after rotation is always there. It will also be an eigenvector. Will it be linearly independent? Then if that is scalar multiple of this one, then ultimately you will show by taking I mean you will take a combination of them and show that ultimately it is not satisfying. It will be there because they are going to have different values. The vector will have different values. How are you choose here? And they are one to one. Some positive and some negative has to be there. So it will have different values. So when you shift it, it will work. So you can try. That is not a problem. So one more rotation to x2 to xn, again xn to x1, and then xn. So these two are linearly independent. And rest of the rotation will be generated by the work of the Iclaa. So if I have one eigenvalue there and one eigenvector correspondingly there, that eigenvector I can use to create two different eigenvectors. Linearly. But that will be a combination of these two. I can still rotate, but that will be a combination of these two. Okay, that we can. That is not good. But two definitely I am getting. So for each linearly independent eigenvector, I will create two. And so what will happen? Uh, the eigenvalue over here for the non-zero eigenvalue over here. So I will have lambda 2, lambda 2, lambda 10, lambda 10. They will come as eigenvalues for this one. This lambda 2, lambda 3, lambda n are eigenvalues of the path. And this one will be, but this is not finished because the total number of conditions was 12. I am missing 2. One of them is 0. That I already. And remember what is the sum of lambda 2 plus lambda 3 plus lambda 4 up to lambda 3? What was the sum of this one? Because they are the sum plus 0 also if you want. This is the sum of the eigenvalues. The sum of the eigenvalues is the trace only. And in the diagonal, what you have, the diagonals are the degrees of the path. And so that was 2n minus 2. That was 2n minus 2. So this whole thing is 4n minus 4. This whole thing is 4n minus 4. 1 has to be 0. And the total trace is 4n. Right? So you will have 1 row. Okay. So that those are the eigenvalues. But I already know actually the Laplacian eigenvalue of wait, there it is. Nah? And then check which two are between. Two. They will repeat. From there, you will automatically find out the eigenvalue. And that will tell that how this one is very small. In that, it was Iclaa in 1973 and 1975 to put that among all domains. The path has the smallest algebraic connectivity. among all trees, the path he proved that, and he then gave that was I think this was for here the electric connectivity was 2 minus twice cos 5 by this is the problem that is found. And he also proved that, he proved that for every tree, among all tree on the vertices, still the part will have smaller algebraic number. Said that. And then there is I think will be a PN or this is, I think this one 2 minus for PN you multiply T. Here varying from 0 to or 1 to 8. So this is this will come out from here. You work out, you will get this one. Because of that, na, that has become 2n. But 2 by 2n, so 1 remains is 5 by 8. Work it out. So the reason you when wanted to tell, one wants to tell that this is connected, that if you are saying this graph has connectivity, some whatever connectivity, two, then when you are adding more edges, it should increase. It cannot decrease. Then only you tell the connectivity, because the sense of connectivity is that the more the edges, the connectivity should increase. Okay, and algebraic connectivity also satisfies that. Okay, that is why, that is not the reason why it is called connectivity. Okay, so algebraic connectivity also satisfies that. If you have on the same vertex set, if you have G1 and if you have G2 and if you add them and create a new graph, that new graph will have bigger algebraic connectivity. And if these are vertex distant, it will be bigger than this plus this. Okay, and that when independent whatever is the connectivity, when they are added, the algebraic connectivity is greater than equal to both of them. Again, added, that is algebraic connectivity of E1 plus E2 is greater than equal to algebraic connectivity of E1 plus algebraic connectivity. With when assuming vertex distinction. Sorry, not vertex distinction, vertex the same edge distinction. Edge distinction. This may sound like very non-trivial, surprisingly, but it is not surprising. Only the man was very surprising and very similarity of time. Whatever we have said, see, of course, G1 plus G2, and what is the relation between LG1 and LG2? Is it solved? What I mentioned? Sorry, let's listen. Given G1 and G2 are in the same set of matrices, but their edge different. Will this be true? Like, like, so I am right in that case. I have like this. So if I take the Laplacian matrix of this and the Laplacian matrix of this, add them. Will I get the Laplacian matrix of this one? That is my question. Hey, see, you want to find out degree? Well, fine. Let us talk about the degree. Degree of what is not degree of this one. Okay, this and now whatever degree it got from the first branch, it got now whatever edges it gets from there, the degree will increase by that only, na? But then that is already captured as a degree here, na? So the corresponding addition will be in this degree. And whatever -1 I am seeing over here, it either might have come from due to G1, it would have come due to G2. Fine. So this part is fine. If this part is fine, then comes the Hermitian theorems. Hermitian, these are all Hermitian matrices. Okay. And so what is the algebraic connectivity? The algebraic connectivity in general, if you are talking about, that is lambda cube is equal to minimum x orthogonal to 1 or 1 step. X norm equal to 1 x star LDX. Now because it is orthogonal to 1, that essentially means it is the space spanned by the rest of the eigenvectors. And the smallest of that will be only on lambda cube that I have already shown. Because any extra x will be a convex combination of lambda 2, lambda 3 of lambda n, and the smallest will happen only at lambda 2, 1 0 0 0 convex. Okay. We'll prove that, na? That max mean kind of thing, maximum dimension is k minus 1 and this one. So here the dimension k minus 1, because I already know it is 1 1 1 1 1, and the other term is minimum only, na? Minimum this also equal to the one vector G1 and minimum of that, and it will be added when you are talking about this one. The equality is added. Remember CFT2? What was CFT2? Lambda J is dimension B, T minus 1, minimum x orthogonal to B, x naught equal to 1, x star is. Is that the one? See the statement you have written down. See the statement. Take yourself. Okay. So here what am I getting? K is equal to 2. And where is it attend? I might have written there when it is equal to only the previous ones, na? So here the previous one is 1 only, na? So x orthogonal to 1, that is where it will be attend in that place. Okay.
So is it a subspace? Pariksha of all ones.
So the subspace over there is that alpha times 1. Because x is orthogonal to 1, x will be orthogonal to 2 to 2 or alpha. So subspace is a one dimensional subspace only. So instead of writing the subspace, these people write it in this way. You want to write me in this? E and B is equal to alpha times 1. Alpha belongs to R. That way. R, C, whatever, one dimension. Okay, so doesn't matter. This is one LGS. But then this is of course is equal to LG1 plus because LG like LG और इसको G बोलता हूँ is equal to this one. So had I taken lambda 2 that is equal to lambda 2 I read that I just substituted LG1 plus LG2 is equal to that. I have not done anything like that. But then minimum of sum is greater than equal to sum of the minimums. Right? Why? Let's say, for example, we could have something like this 1, 2, 3, and then 3, 2, 1. Minimum of the sums is 4, but sum of the minimums is 2. Because the minimum over here is 1, and the minimum over here is 1. Sum of the minimums is 2, and minimum of the sums is 4. Why the say minimum in this set and this set? If you are adding term by term, at the best the minimum and the minimum they will be in the same situation. In that case, that will be the solution. Otherwise, the minimum might be aligned with something else, so their sum will be different. So therefore, using that, this is the same thing. Like minimum x orthogonal to 1, x norm equal to 1, x star LG1 x plus 1 x orthogonal to 1, norm equal to 1, x star LG x. And this is nothing but lambda to LG1 plus lambda to LG. Hey, and that is what this fellow said. Ultimate connectivity of this. And this is a nice thing because of you see I have put 5 rupees and I have put 10 rupees also. Minimum it should have it in 10 rupees. Like if you because two things are coming together, so there is an additional advantage that is fine. Otherwise, the minimum it should have is like it had this much of connectivity, this has this much of connectivity, two things are put together. The minimum connectivity, like, so that's what it is satisfying. Okay. Plus, there is one more that you should know. It is not just about the algebraic equation, but about any element. If you have a graph T and I have two conditions, and assuming that I and J were not conditions, there is no H. You have a graph H. And then what you do? You add. So essentially what you are doing, you are adding this. So what is the change in the Laplacian matrix? Now the change in the Laplacian matrix. The Laplacian matrix. In the Laplacian matrix, this is LG plus a 1 minus 1 minus 1 matrix in IJ, IJ. Other places too. Because that degree will increase by 1, this degree will increase by 1. This edge will appear, this edge will appear, this is the same. And notice that this is a ramp 1 positive semi-definite matrix. This matrix is a rank 1 positive semi-definite matrix. Okay. And therefore, what you are talking that you have a Hermitian matrix and you are doing a rank 1 positive semi-definite population. Got it? And then in what happens to the argument that interlacing is also true. That one is quasi-interlacing. Quasi-interlacing is about bordered matrices. If you have one Hermitian matrix and you just bordered it. There is another kind of interlacing, which is this interlacing. Say, you have a Hermitian matrix and you are adding a rank 1 positive semi-definite matrix. A rank 1 positive semi-definite matrix what look like this one. Or if the rank 1 positive semi-definite matrix not look like this one. Vector on zero vector. Star. And here what is it? Now this one is actually all you have to do is like this. 0, 0, 0, and then minus 1, 0, 0, and then maybe 1, take 1 over 0, 0, and then multiply the 0, 0, 0, and then minus 1, 1, 0, 0. Okay. That is it. Minus 1 into minus 1 in the result will get 1. Minus 1 into 1 will get minus 1 into minus 1 will get minus 1 into 1. Okay. And in this case, I didn't use interlacing. In fact, not only the I didn't use interlacing, forget about the interlacing. Each eigenvalue now increases. Here it increases because you are adding a positive semi-definite matrix. Each eigenvalue takes. Okay, so in particular, when you are adding an h, each eigenvalue, each Laplacian eigenvalue, we can take only. That is how. Of course, you can directly apply the previous theorem to tell that because you are adding edges, the algebraic connectivity will increase, but that is only talking about the second smallest addition. Here, because you are adding a rank 1 positive semi-definite matrix to any Hermitian, the eigenvalues can only. Rank 2 whatever, sir? Yes, like whatever that tells, it is automatically like applying pricing. Whatever that tells, it is automatically like applying it twice. You want to read more about it, uh, and more work, you please see Horner Johnson matrix analysis book and Agia's matrix analysis. He was more interested and he is more interested in, and there are many other inequalities, equalities, what happens under perturbation. He is very much interested in it. So those two are classic. And if you can, like if one can follow a little bit of them, and that whole life will go. If you are okay. These are very good books. One and Johnson matrix analysis and matrix analysis by yeah. I mean, Laplacian makes it very smooth because it is random. Actually, depending on the matrix that you are nowadays, people are talking about some AR that kind of eigenvalue, which essentially means instead of taking D minus A, you take some alpha times D, where alpha varying between 0 and 1, that kind of thing. And then consider many things. These are like part of Laplacian matrix. In part of Laplacian matrix, we can consider any real diagonal matrix. And even the part of Laplacian matrix has many properties similar to the right. So, probably we will only require whatever it is there. I don't think anybody like they are talking about Laplacian. So if you are interested, read that 1994 percentage. Okay.
So before the deal, first of all, I would like to thank Dr. sir for giving a series of lectures and handling the tutorial sessions for the last 2 days. So by this session, sir is completing this lecture series for this workshop. So we from the Carol side, we thank sir for giving me a wonderful talk. Sir. Thank you. So I request Yogi sir and Mandana sir to please honor him. Sir, please.
Back he was with us in 2012. At that time, he was fighting and now it's already. I personally thank him for please, please, let him give the slide.
So I request Raghavan sir to hand over the certificate to Dr. Singh.
Not yet, I have that training. These are all people. People might have already made these first. Anyway, you'll have formal definition. These are.
The like old money. We all have practice.
Professor Rahul also because since the 2012.
So now we will have how many of the that after the. He was coming to me 1 month earlier, and he became our faculty. Wow. Yeah. Okay. But taking exam, yeah. No, here I could talk. He got that's why. So, they were. I was, I said. This guy is immediate for support. But then, you are going to make a deep work. So I I could not make him. Good. Good, he went back. You don't want to lose it. July. The other Right, over. Production, that would be that. But it has to be, what I could talk about those things also, but it should be what my own city was bad. If you could, this one, so where do you? But there was one thing you say, no one, listen. What do you, that's making a property. That's why. Because this is not getting operated. It's something that I about to say. But we can not this application. What we can be all the existing detail existing is different from other than the everything everything. I didn't look at the approach like solution, but why positive and not your existence approach. People are not, they don't go in a values that, yes. Activity, they are probably. So that's why sometimes when you may not necessarily be able to cook formally everything. You could do only on large area, that's part of the problem. But I also want this, the reason why I work on you. I had a long fight with the husband, yeah. He was mediation. And mediation 62. Not the case with the that I say that word in the future. And the issue is people have the people. So you know, for a lot of time discussing other things. Such a right question. There, we should have so you have a lot of energy. The one who, I think that is today. Last week we went to office service. There is one person, his name is Patrick. He's from Iwsmga fishing. He is a graduate from office. He had one paper with in 1980s or that. He wrote it, it is the Indian this about the care officer. He is now 84 or something. He is there in Amos also. Amos has some old people. Surname is that thing, I don't know, something. This person is from Patrick, I want, in this, I basically, he was a functional. Yeah. Everybody see the thing is, the dominating structure is he was to I used to provide city or working this. And no one. It has some close to where it's very, not better, no less than. Yeah. There's some incursion, and that's useful. All promoted if the from position. And then to the beginning. He was to person to here, what's the water? Who goes before, who go walking? I think both done. You should, I'll get the thing to for yes or no. I have the big. That's why always another always no. But I hope because it's I don't agree for I hope there will be connection with the otherwise, oh, sir, you can't play as a wife. No, sir. Then after this, I did. This is it. So interested can offer sir, there will be taken for, there is the guide of our sir and direct student of CR, process CR. I think I am audible. Good morning, everyone, and the relationship between after evening time, managing serves to manage the reading center. He currently serves as honorary visiting professor at Iclaa, March 2025. He previously managed the reading center from 2020 and held key roles in the and war in. With a PhD from Iceland, he is also for applied statistics, linear and nonlinear programming, games, statistical quality control, Six Sigma, and quality management. He has published notable papers in tiling games and applications, and also books like Modeling, Computation, and Optimization, and Mathematical Programming and Game Theory for Precision. He was also contributed as a resource person at conferences such as the Market, Computation Optimization, and the ICECW UK conference. Also, we have been associated with them class from a very long time, starting in 2012 with PFD. So, let's welcome Professor Yogi. So, thanks for nice introduction. So, before I start, I would like to know that the distribution of the participants, that mostly that between the from where you work and which area you are working. Quickly. Okay.
I'm the
Okay. 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 Next. Oh. Next. Thank you. Okay. Okay. You are from?
And
Sure, okay.
it's just really particular.
Okay. And yes. You are from which area? Academy. So, but you are working on some area.
I'm working.
Okay. So next. Gas and matrices. Okay, very well. Okay.
Srinath, matrix C.
Okay.
Swarna, neighborhood and domination.
Data.
Neighborhood and domination. Anusha algebra.
Sir,
Sir, I was doing this.
Which area?
Sir, maybe I have 6 students.
Oh, in the small matrix. Matrix. So you are from? Oh, okay. Yes.
Sort of algebraic.
He was algorithm industry.
He went back to it.
Check for asking for.
She doesn't learn.
Yes, matrix. So as I can see that almost 70 to 80% are from spectral graph theory and remaining are matrices. So that comes, you know that whether you work in a graph theory and or spectral matrices, these two areas have close connections. Many of the results you can interpret on special matrices you can interpret in terms of graph theory. In fact, that many results that from the special matrices are come from graph theory. So these two areas are interconnected, and many times that proofs become easy. That if you are looking in terms of say graph theory angle or graph theory converted matrix theoretic angle. So these two areas are complementary to each other. Okay. So as is mentioned that I'm associated with carers for a long time, and here some specialized workshop is arranged, and those who are primarily devoted to special matrices and you will find hardly any kind of workshop which are devoted to special matrices, which also arises from graphs. Many of you know about PD matrices, positive definite or positive scientific matrices, and there is a nice book by Sir Rajendra Ghatia, biased there, so you might have studied that. It's a nice book on PD matrices, and now there are a number of generations which has happened over the years, over so many years, last almost 5 decades. People have done generations, and these special matrices have special applications, and more than 50 or I will say rather 65 to 70 classes of matrices exist as a special matrices. And around 10 or 15 of those special matrices are introduced by us. And remaining are not, but from US, Europe, etc. So I said there is a very big group who are working on special matrices and graphs. And I will be talking about, I cannot cover all those special matrices, but I can talk about some of the special matrices which has applications also in various areas like optimization or game theory. Because once you try to publish something on special matrices, mostly in the papers that when you submit it to a journal, they will ask what is the application. Okay, so we have to justify the applications, whether it is in the application, it has application in statistics or other branches of science. Okay, engineering or economics, other branches of science, they will ask. For example, you might have heard about G matrices, where off-diagonalities are non-positive. So it has lots of applications in economics. In fact, it originated from economic applications. Okay, now I'm going to introduce some of these special matrices, and some of my special matrices. You know that for the characteristics of those special matrices, you require some special kind of tools, and there are tools, that comes from linear algebra. So you consider a linear system, and you may see in a particular angle, and many of these matrices are associated with some linear inequalities, with the problem of linear inequalities, which is known as linear complementarity problem. Okay, so this problem of linear inequalities is very old. It came from algebraic graph theory, and it is 1940. So some of those classes are originated. And after that, it was introduced and considered by many authors, many other authors. So the new classes of matrices. So I'm going to speak. Okay. You know that why a matrix is called positive symmetry? If given a matrix A, if X transpose A greater than equal to 0, it is non-negative. For all X belongs to Rn, then you say that matrix is positive symmetry. In short, you say this PSP. Okay. Now, if you have a positive symmetry matrices, what are the properties? If diagonal will be non-negative, right? And you see the repair of positive symmetric matrices, they consider symmetric one. But it is not necessary to consider it. There is a reason. You know what is the reason? Because the x tends to x is half of x tends to a plus a tends to x. So because of this reason, you can convert it. You can convert it. So that's why that is the reason that you consider symmetric matrix. And if it is strictly positive for all non-zero x belong to R, then it's a positive element. And these two matrices have applications in optimization, games, statistics, everywhere these are the applications are there. And that's why that it has gained a lot of popularity. And one of the applications is that if you consider the optimization problem that minimize fx subject to some set, not some visible set. Okay. Right. Subject to. If you want to minimize a function from Rn to R, if it's from Rn to R, subject to
that the point from a feasible set which may be convex one. And in order to prove that A is convex, you need to prove that Hessian matrix is positive symmetry. Okay, so that is one of the applications of positive symmetry matrix. Okay, so that is the equinoly type of conditions. So you need to evaluate the Hessian, and this particular result has lots of applications in economics, optimization, game theory, everywhere it has applications. Now, if you look at positive symmetry matrices, if you look at positive symmetry matrices, you see diagonal elements are non-negative and all its principal submatrices. So, what are the principal submatrices? So, these are the, if alpha is 1, principal submatrix is this. Okay, and principal submatrix is determinant will be non-negative. And also that it can have a that you can take half of Iclaa data to make it a symmetry, and if you evaluate all principal submatrices, so that is good enough to check. Is it? It is positive symmetry. But if the n is very large, it is not very easy to check. So then you need some mechanism to test it, which is there, that there are many algorithms are available, nice algorithms are available. This one is a good algorithm to check. To figure it out whether the matrix is positive, symmetric or not. Okay. I will just keep this and bring it later. That sufficient and all. Okay. Okay. Now, positive subdefinite matrix. Positive subdefinite matrix. Subdefinite matrix. It is called PSOD. This was introduced in 1969 by Della Matos, and so how to test whether the what is positive subdefinite matrices? You compute the x times for the x, and if it is less than 0, implies a transpose x is unisign, then you say it is a positive subdefinite matrix, and it is a generalization of positive subdefinite matrix. Okay, so this is the example. So you see that this matrix has diagonalities, non-negative, and what is the determinant? Determinant is positive. Now you see here, but you compute x stands for the x. It is not greater than equal to 0 for all x. We learn to Rn. So here, but however, here that x stands for the x, that equal to x1, x2 is less than 0 implies x1, x2 are, if it is opposite side, then one is positive, one is negative, so it is the opposite side. And so if you take x1 is positive and x2 is negative, you can see that a times to the x is this, and if x1 x2 are opposite signs, then it will be unit sign. Clear? So this is called positive subdefinite matrix. Okay, it's a generation of positive semi-definite matrix. So now you can have a graph where this kind of matrix arises with entries 1, -1, etc. What is PSPD? PSPD means X transpose X less than 0 will imply A transpose X is Iwsmga. That means A transpose X either is less than equal to 0 or A transpose X is greater than equal. Right? Now, you can it is so whenever X is for any X that whether it is non-negative or any sign doesn't matter. So whenever X transpose X is less than 0, it has to be unisigned. Now the assignment is that you can construct a graph, this property holds. It can be elements of 1, -1, 0, 1, -1, you can take that way. So you can construct a graph for which this property holds. Right? So this will be the afternoon, we talk about it. So afternoon I have something first, is that you? Tutorial. Okay. Now we can see that PSD matrices, positive semi-definite matrices, if A belongs to, then A plus A transpose also. Has entered. So that is side of the chalk is wrong. This is very good. Yeah. So for PSD matrix, this is the property that if A is PSD, A plus A transpose PSD. My next question is whether it holds for PSD matrices. So this is the counter example. Okay. Now what happens in matrix analysis? There are many results which holds for 2 by 2, but it doesn't hold for higher order. So construct an example of order C. So you write down this as the assignment for the next tutorial. Construct an example of order C that where A is PSPD, but A plus A transpose is not used. Okay. So now you see that this is if and only if condition. If and only if condition. So here you can see here A plus A transpose is PSPD. But A doesn't belong to it. Okay, so for 3 by 3 example, you also check. So construct an example for which A plus A transpose is PSPD, but B belongs to PSPD. So this is a very basic property that of a PSPD matrix, which holds for PSPD matrix, but it doesn't hold for PSP. Now, many of you know about what is principal minus. Right? So, a large jump of people are from spectral graph theory. So, principal minor have defined if alpha is the subset of 1 to n, then A alpha is called a principal submatrix. And this principal submatrix has a very big role for recognizing a large class of matrices. Okay. So if this is a matrix, and if alpha is 1, 3, so this is one of the principal submatrices. So how many principal submatrices will be there? For a 3 by 3 matrix? You see, diagonals are alpha, you can take 1, 2, or 3. So there are 3, and then 2 by 2 there will be another 3 and matrix itself. So you will have 2 to the power A principal minus. Right? And if it is very large, it's not very easy to check through this. Okay. Now I will introduce another concept which is called principal pivot transform. And it was introduced in 1963 by Tucker. So, what is principal pivot transform? You see that if you partition a matrix, then alpha, if you partition a matrix like M alpha alpha, M alpha alpha 1, M alpha 1 alpha, and M alpha 1 alpha, and take a principal PPT with this respect to alpha. So, what will be that PPT? M prime alpha alpha will be M alpha alpha inverse. M prime alpha alpha, that means this one will be minus M alpha alpha inverse M alpha alpha 1, and M prime alpha 1 alpha will be this, and M prime alpha 1 alpha 1 will be this. Now this M prime alpha 1 alpha 1, this has a special name. Anybody knows this? What is the special name? Soon complements. So this has a special name. It is called soon complement. In matrix algebra, we took many results on that. If this is a matrix, its soon complement also will be in that class. Okay. So soon complement also will play a big role. And how do you write principal pivot transform? We write rho alpha or P alpha, the bracket M. So this is principal pivot transform of M with respect to alpha. So this is a common notation which is used in matrix algebra. So let us take this matrix, and I want to find out soon complement with respect to alpha equal to 1 2. Okay, then soon complement will be this. I can compute all these quantities, and then I can compute them soon complement. So in the afternoon, we will have we can have an example that where we can compute all the soon complement. Yes.
Is there any other combination that
Inverse is
inverse is the most
And
Mark
A mark for the inverse.
Is there any assumption?
I do not follow what you say.
Assumptions of the matrix.
Assumption of the matrix, okay. You see that if the matrix is singular, obviously there will not be PPT with that alpha. So PPT is defined only when is that particular submatrix is non-singular.
If already exists, will not be there.
So this when a matrix is non-singular, there we will say non-trivial submatrix. That will name it as non-trivial submatrix. So you can evaluate PPT only for non-trivial submatrix or alpha. But that was another name. It is called legitimate PPT. Tata calls it as legitimate PPT, for which we get yes.
And if we can use movement or also.
Yes, that you can have a generalization of this PPT as well with respect to more variables inverse, and this all is the range of the results. You can extend it for more variables inverse. Perhaps that not much work has been done. So people can look at the results which are for the singular matrices. No, so those results can be easily extended for more variables inverse, and you can have a quick paper in that. Okay. Not only that, as I said that you will see that as I said that Bhattia's book, you will see, or even if it's linear algebra, analytics applications, LAA, that there are plenty of papers now also in appears on PDPS analysis. Now, is it a good idea to generalize? So generalize that many of the results which occurs for or which holds for PDPS matrices can be generalized in terms of PSD. Okay, this is not this one, no, that is this workshop. I cannot give it in a tutorial, this is a research problem. So you can go through I think Matthias' book and see what are the results. We can generalize it in terms of PSPT matrices. But you have to be very careful. You have seen that when A is PSPT, A plus N transpose need not be PSPT. So you have to be very careful of generalizing it. And I am sure a large number of papers can be produced by research scholars if somebody is working in this area. Yes.
There is no characterization of PSPT such that it will take the main.
No. So this is another problem. Under what condition? Under what condition that if A doesn't A is PSP, then A plus it has to be PSP. So if you like that, you can look at I will produce a lot of results that you can put some condition and then prove certain results if it doesn't go. Okay. Now you will see that I was talking about special matrices, a large number of special matrices that is involved in connection with a problem, which is basically a problem on linear inequalities. I can have some slides. Can I go to that slide? I don't know whether it is there or not. This this is probably not a modifier, maybe it is not yet. Okay. I was showing you an algebraic system I just see 2, 3 slides and then so on. This I have taken from some other talk. Maybe that I understand that they have given time. So the time permits that there is how many of you ever finished your many of the spatial matrices results or graphs converted into matrices. You can get a lot of characteristics from daily theory characters. So if time permits, that then I will talk about those slides also. So it is there, but at least some part I will be using. So you will see that often that when I will be talking about spatial matrices, I will use a algebraic system. Uh, it's a system of linear inequalities, and there is a one condition which is called complementary conditions. Those who have studied linear programming, when you talk about duality, so what is there in the duality? It is primal feasibility and dual feasibility and complementary slackness. Okay, so these three put together, so they are called Produce-Critical conditions. So this condition holds in a more general framework when if it's complex and if you are linear and equal, you can have that kind of framework that it can be described by Produce-Critical condition, which is in short, which is called KKT condition. And many of you heard about Produce-Critical conditions. So this KKT condition, Produce was a student library, and they wrote the paper with critical condition, but when the paper was published, perhaps that Produce name was not there, so there is a protest from the academic community, and then all three names are put together, and it was, you see that in the old book it is written as only critical condition. But later on, the current books, all everywhere it is written KKT condition, Produce-Critical. And it has a huge implications, not only in matrix algebra, in other those who are working in computing, not that you will see that lots of interior point algorithms, so that kind of framework is used for computing. Okay, so instead of diverting it, so let's concentrate the topic. This problem provides a unified framework, and it is an application mathematical programming, and I just keep certain things. And I wanted to tell you that this problem from where it came. It came because introduced by faculty to help the unloading problem plane curves. So this appeared in 1940, and in fact, if you see that whatever is there by name linear complementary problem, so that appears also here. But the notation which was used by Patrick to help is a very old notation. I have given to some of my students who are who used to have some summer course to convert that to rewrite their own latest notations, and I gave them as a project. So these are the Patrick. Okay. Then second was single term. That problem that was called as a problem of linear inequality. And in quarters, this is and later on they call it as linear complementary problem. And this name became very famous that when Lenzing was used for computation of equilibrium point, and after that, once Lenzing, that is a beautiful geometry. I think are you going to explain it? You're going to no, you are not going to explain it.
No, I'm going to
Yeah, okay. So and later on, that is subsequently modified by Lenzing, and the algorithm is called Haus's name is no longer there. and it was called Length algorithm, and the computation of Iwsmga came that the algorithm is also specialized in this framework. Okay. And it is 1965 paper. You may wonder that it is 1965 paper and it is 2025, whether anybody working on this. There are plenty of people in UK that I find that they are working still works on linkage algorithm and polymetric on biometric scheme and polymetric scheme. Okay.
Go back to the slide.
No. I want to go back to. So you may like to see how practice used to look like. So I could get a photograph of practice who wrote that paper in 1940. So have you seen this photograph? Okay. So this is the paper that unloaded problem of land curves. So you can look at that paper. I think you search Google, it will be easily available. So it is a good idea to rewrite that. So you can see that Iwsmga, who gave the name as problem of linear inequalities, and this is the Iwsmga's photograph, and this is a paper by him, a problem in linear inequality. Okay. This process is not man. So you will see that similar kind of structure is there. Okay. And later on, you see that dancing plays a dancing, many of you know that who plays a big role and development of linear programming. So in terms of simplex method. And so when simplex method was many of you know what is simplex method? Okay, so simplex method is that it's a that everywhere that might be teaching out the simplex method, no? That's in many courses, or you might have attended some courses where the simplex method is taught and linear program. Okay. So it is given by Tansky. Okay. And by the simplex, you know that simplex birthday was celebrated. So in 1997, simplex birthday was celebrated in Switzerland. So in a conference on the International Symposium on Mathematical. And here there is a I heard while coming that your PhD programs now it is 3.5 years. So you may consider that whether it is feasible or not. So let me give an example that so when Daxi was attending the class, that something was written, that in the board, and those days that now people also come late, but those days that Daxi came, almost classes is over, and there are two problems which are written, and those happens to be that he solved those problems, thinking that there is a homework, and that was later on a smart mistake. So it is feasible that to write a thesis even within a year or maybe better, but you have to be like him. Okay, everybody cannot do that. And this is a famous method, and the Lemke he contributed in the literature, whether it is whether it is linear algebra or game theory. So he has contributed, or optimization, he has contributed every lecture. So this is a photograph of Lemke. This is very rarely available. And by the way, that he is a boxer. Mathematicians that can be a boxer. He is a boxer, and so these are the two papers which made him famous. To become famous, you don't have to write so many papers. So it has to be like Lemke, that he wrote only 25 papers. but all are jets. And so this is about like that all these this is for motivation purpose that they show us the part, no, that what is important is the quality, not quantity. I think that before we move further, okay, we let me cover the linear combinatorial problem from this. So here you have given a matrix A, okay, and a vector Q. Matrix A is of order A by N, and you have internal vector, and you have to find W and Z. These are it has been converted. Actually, it was an initial list, but these are converted to that equations, and this condition actually satisfied. Doctor Sujay actually satisfied. Okay. And I think I'll go back to the previous slides. Before I go further on this, I'll go back and what are the five students? Yes, sir. I will be. I will be eligible. So let's go back to the question. Okay. So linear complementary problem, it can be that originally it is written in this form. So we have a set of linear equations. You have solved linear equations, but have you solved any kind of linear inequalities? Yes or no? No. So how linear inequalities will solve? So when you solve linear inequalities, you get a feasible point. You get a feasible solution. And that feasible solution can be computed by, I mentioned a simplest method, page one of simplest method, you can get feasibility. Now that if that feasible solution also satisfies the third condition. So if say suppose Z1 is 0, then corresponding first inequality has to be Z1 is greater than 0, then first inequality has to be 0, equal to 0. Okay. So this is called complementary condition. And you can put that primary well, or you write down the equity condition, or you can put it in this way. Okay. Now, if something satisfies, no, if Z is greater than equal to 0 and Q plus NZ is greater than equal to 0, then you say it is a feasible solution, and the set of feasible solution is called a feasible set. And so basically, you have to find out W and Z. If you write down W equal to Q plus NZ, you can write it in this form. And you have to find out W and Z such a way that whether you get a solution or no such W and Z exist. And you can get this using Lemke's algorithm. Okay. As I said, that it comes from linear programming. If you write down primal and dual, and then if you use the complementary slackness theorem, then you can put it in this framework. You can put it in this framework. Now, why I introduced linear complementary problem? Because you get the matrix same from there. No? That I said that it is solved by vector. But matrix A, that unless it is a very special structure, you cannot use lengthy diagram. So large number of special matrices that came from the point of view of computation by linkage diagram. Okay. And those matrices are called Q and Q matrices. Q matrices means that whenever that for any Q, you will have a solution. That solution set will be non-empty. And Q naught means if you have a divisible solution, then you will have a your solution set will be non-empty. So these are the two classes that which came from these two special matrix class which came while studying linear programming. You see that a matrix M is said to be S matrix when if there exists vector z greater than 0, such that z greater than 0, and so this is called S matrix. And it is easy to see that if you look at the relationship between Q and Q naught, so Q equal to Q naught intersection S. If it is matrix M is both Q naught and S, then say it is Q matrix. So which will guarantee that it will have a solution or any Q belong to R. Right? So when you solve any problem, that what you see that whether the problem at all it has a solution or not. That the existence of solution, no? That so Q and Q naught matrix plays a very big role while you draw the existence of solutions of that system. Okay. Now I will come back that I was introducing you principles of matrices. Now if all the determinant of all principles of matrices, that is principal minus positive, then we say it is a B matrix. Right? And this B matrix has a special feature, okay, that if you denote M2 is the number of solutions and if M is a B matrix, then it has solution only one solution. So wherever you lies in R, that you will see that you will have always a solution and the number of solutions is only one solution. So that means that if it lies any one of the complementary cones will not be overlapped. So it will be only one single complementary. And this is a very nice result that Samuelson and et al. So they gave the result in 1958. And later on, Monti and others put it in the complementary paper. Now we will see that Horn and Johnson, second column, that you will see they refer about P naught matrices. P naught matrices. Okay. So P naught matrices that if all principal minus are non-negative, then it is called P naught matrix. Okay. Now can you find a so now the open problem is develop an algorithm other than looking at the principal minus. Develop an efficient algorithm. I won't say whether it is a polynomial or not. Develop means the possible polynomial algorithm. You cannot take it. Or recognizing whether the matrix is P or Q. Okay, so this we cannot do with the system, no? That integral system. Okay, so this problem is open almost 30 years, 30 to 40 years it is open. Okay, there is no algorithm, nice algorithm known for P or Q matrix. But as I said that if I put some condition, no, then I can talk about some polynomial algorithm that I talk in the session later. Okay. Now this is that 75 years of copositive matrix. So copositive matrix is said to be copositive if x tends to the x is non-negative for all x belonging to Rn class. So x greater than 3. So in the detail session, construct a 3 by 3 example matrix copositive. Construct a 3 by 3 example copositive. Right? And A is said to be strictly copositive if x tends to the x greater than 0 for all x greater than 3. X greater than 3. Now you can see here if all if it is a all entries are positive, then it is a strictly copositive. And if it is non-negative, it is a copositive. So in the example I will construct, so that should contain some minus. Now A is said to be copositive class. If every A is copositive, and further this additional implications of x tends to the x equal to 0, x greater than equal to 0 implies A plus A tends to the x equal to 0. So this is one special matrix class which has a lot of applications, and this who was given this class that it is used by NK and it is developed by the Portal. So they have a joint paper, Portal and Iclaa and NK, so they have a joint paper whether when they came up with this class, and this class mainly came from the application of Lemke's algorithm. So if you see the literature, the Lemke's algorithm gave a lot of push to come up with the lots of special matrix classes. And matrices cooperative star if this implication holds. So this is another class of matrix. So that is if a matrix is known that if it is a cooperative star, then the Lemke's algorithm goes. And it has lots of applications in optimization and games. Okay, and there are references no, that this kind of matrix array is also reactive. So you can see that this is a copositive matrix. Next one is a strictly copositive matrix. These are quite two trivial examples together. And this is a copositive matrix, copositive star matrix. So one can check that at least. You see that if M is strictly copositive, then that the system of linear inequalities which I have shown, no, that those will have a solution, the test will have a solution for each Q belongs to R. I have known when the matrix is a P matrix, they also will have a solution for each Q, but their solution is unique, but here uniqueness is not correct. So if you drop the uniqueness assumption, then this is one of the class. So where but if you take any Q, choose any Q, then this will have a solution. This system will have a solution. And Now, in game theory, that we do not typically, we do not require for all. We need for very specific. So you can come up with many stochastic game formulation where between 0, 0, 0, 0 only there's -1, -1, -1. So that in the formulation, that kind of special Q array. Now, it is not necessary to get a stationary equilibrium points or value vector. You need that kind of that for all people do not need, and that is a very strong assumption. But if this holds, then there will be computations. So what you need basically this p greater than equal to 0, p greater than equal to 0, beta to then be equal to 0. So this is a condition of a, you see later on, this is a condition of the Arnold matrix. So it has to be Arnold matrix, and apart from that, it has to satisfy beta to be greater than equal to 0. Then if this condition, if you check this condition and if this is valid, then you can say that there is. Now, I have talked about Pinot matrix. So Pinot matrix in the there in Hall Johnson book, no, that there are one part, first part is matrix analysis, second part is topics in matrix analysis. Okay, so there you see that section about Pinot matrices. Now, polar sufficient matrix is subclass of Pinot matrix. And you can check that this implication holds, then it is a column sufficient. Okay. So again, that recognition problem that check whether the matrix is column sufficient or not. So that is a one can want to look at. Okay. And okay. And if you take M transpose, and that also happens to be column sufficient, then you say it's a closed sufficient. And it is not necessary that a matrix is row sufficient, then it will be column sufficient, it is not necessary. And so this is the example, counter example, it is column sufficient, but not row sufficient. One can check. Okay. Can you that constant example, the 3 by 3 example, that for which this concept? And while talking about this row sufficiency, column sufficiency, it has some special properties. Can you identify one or two special properties? Okay. This row sufficient matrices, this kind of special matrices, nice applications in optimization. So if A is a row sufficient matrix, and for each vector you have this is a quadratic equivalent problem. And if you take a Koroskutka pair, if you have a row sufficient matrix, and if you take a Koroskutka pair, then that will solve this. So that means that the minimum will be that the data should that Q plus N AJ will be 0. Now you will see that the Sivakumar will talk about geometry. So this is a permanent Leonard's book. So there is a space that lots of chapters are devoted to geometry. And there is a chapter, last chapter. I think the last chapter is on the problems I'm talking about. Many of the results you can find in permanent levels non-negative matrices. So the last chapter, whatever the content I'm talking about, it's a the starting point is there. Starting point is permanent levels book or not. Okay, and somebody was asking, that whether you can add a this one, that if you use generalized inverse, you were asking that the generalized inverse, the use of generalized inverse. You are asking, so I advise that you can go through that book and then you start that whatever the problem I have listed, you can do that. Now, from 1970 onwards, that 1970, many people worked on that for this spatial geometrics that algorithms for linear complementarity improved. So one is the Chandrasekhar's as a nice name. One use simplest method for if it is G matrix, then we can compute by simplex method. And if you see that Mangasarian's work, that Mangasarian wrote that such kind of if it is G matrix, then we can solve it as a linear two-line problem. So lots of work is devoted to that. Okay, so this is a formulation that can be written as a complementary form. Linear complementary form. Quadratic programming can write it in this form, and here that this I am talking about the quadratic program. Here Q has to be positive symmetric thing. So then if it is a convex quadratic programming, you can compute solutions using that. And for bimatrix thing, also that make all of them are aware of what is bimatrix thing, right? I will not get into that because it is a diversion. So for computing Nash here, you can use this formula. And here the M is given by 0, A and B are the pair of matrices. A and B are the pair of matrices. And your Q is vector of all ones. And you can compute that for this using language algorithm. But you may wonder what kind of matrix will be there, that A and B transpose, 0 A and B transpose. So this we can discuss later on, that what kind of matrix it is, and okay. Now while studying these matrices, complementary codes plays a big role. Okay. I said if you write W equal to Q plus MZ, so this you can write I W plus MZ equal to Q and W plus MZ equal to. So this condition says that when you have a basis matrix, all of you know what is basis matrix. In simplex, you know about that they have come across with basis. All of you have started simplex with that.
The matrix for the basis of it.
Basis matrix.
for the basic service,
Basically.
basically.
So you have say there what kind of how do you write down the syntax method that can? How you write it down the syntax method that when you use syntax method, what happens basically? So you move from one corner to another corner, and basically that you move from that those extreme points, and if the solution is if it is a solution, no, that physical solution, so that you get that it moves from one corner to another corner, and which optimizes the solution, so that is the from the basis which will get, so that so that is your the optimal solution. Now that you know that many of the this one, a large amount of literature is devoted of form start. Have you heard of form start? So one start is the recent topic, you know, people who are that instead of that taxi kind of basis, that we start with the basis where you can reach to optimal solution faster, right? So you can skip certain steps, and here that lots of machine learning algorithms are used. That for similar problems, you know that you learn it, what should be your basis, and once you know the basis, so that would be a starting point. And you run the algorithm and reach to the solution faster. And that is required if you have a that for large scale optimization. For large scale optimization, you cannot do it additionally that take I mean simplex method you cannot use it. Simplex method you cannot use it because you get into the problem that many this one will require lots of inversion, matrix inversion, and it will be close to simpler matrix and you get into that. So therefore, that you have to skip. This is a good idea to skip lots of corner points, and you arrive at start from a corner point which is nearer to the optimal solution. So you can move like that, and many of the interior points. This idea is used in many of the interior points algorithms. Yeah, all of you have a hard out by the way. Diversion. Parameters algorithm. Parameters algorithm. So that is the say I will say second interior point algorithm of algorithm. So you can look at that paper. That Karmakar is a brilliant guy from IIT. He is IIT product, by the way. So IIT Bombay product. So he was the electrical engineer, and who essentially told us that you know that idea that if you have that field, no, that so you need not reach from the this one through the extreme point. You can reach, go from inside and reach to the other corner faster. So there are some positions that one can use it. But problem was that even though he gave that algorithm, there are lots of you may be aware of that there are lots of politics was there, and they didn't allow government to come up. That whatever that credit is reserved, and particularly this there are two groups. So one is that those who work on the classical one, pivoting algorithms, that pivoting group and then the interior point group. No? So there is a for big fight. And when Permanent wrote the software, it was sold only 2 copies are sold. In fact, that Permanent in the beginning, he gave the exact price. All of us, those are like that went to attend the Permanent travel when I said there are many workshops like this was arranged. And later on that people what they used to ask, typically that very uncomfortable question. What kind of question? did you use a special trick in your programming trick so that you are showing it in the faster? So that kind of question, no, he used to be annoyed. No? And it is not only that however he is present, so that kind of question he faces. But we believe that that is a brilliant idea. And even the small problems, no, that doesn't work very well, but for larger problems it works very well. And lots of that bigger the research of which they are conducted. Okay. Okay, so as I said that you can write this, so whether it is a linear programming or quadratic programming, anything that and if it is a linear programming, this M is a positive symmetry matrix. It is a positive symmetry. So here, if you write it in this form, that IW minus NJ is equal to Q, and we can talk out the cones, complementary cones, and Q that you are getting a solution means that Q is in that cone. Okay. And I first give an example and then go back to the definition, the inverse definition. Suppose your aim is like this. Okay. And if you write I minus MJ, so minus M is minus M dot 1 is the first column of minus M, and second column of minus M, and then I dot 1 and I dot 2 is this. Now, if you write down the cone, I minus MJ, that I was talking about the basis one. So, if you want to have a solution that this problem, if you write it down, how you can write it down? W1 is equal to W1 minus 2J1 plus J2 equal to Q is not big, is equal to some Q, equal to Q1. And W2 minus 2 minus J1 plus J1 and minus 3J. Right? And so in order to and W1 J1 and equal to 0, W2 J2 also have to be 0. Right? So which essentially means that if I write down with the matrix form 1, 0, 0, 1. So whenever W1 will be there, J1 should not be there. Right? So those are called complementary bases. Those will have those are called complementary bases, and you will have two square complementary bases. So therefore, what are the complementary bases? I dot 1, then minus M dot 1 will not be there. Then it will be I dot 1, I dot 2, and I dot 2 minus M dot 1 and minus both W1 W2 is 0, then J1 J2 positive. Is it clear? So these are the four bases. Yes? Yes or no? Not clear. I am asking a solution of this linear system. You know, all of you know how to solve a linear system. But here I am demanding something more. In this linear system, how many variables are there? W1, W2, J1, J2, 4 variables are there. Right? And you will have two equations. So how to get the how do we solve such systems? You will have you can use find the you can find out using inverse. So you can put J1, J2 is equal to 0. That will be one basis. Then W1 and J2, W2 is equal to 0 and right. J1 is equal to 0, J2 is equal to 0. Then W1 is equal to 0, J2 is equal to right. And so in other words, if you take this pair, only one of them has to be in the basis. Only one of them has to be in the basis. So I will get the basis matrix. So in terms of complementary cones, so I dot one, I dot two, so this is one cone. I dot one minus I dot two will be this cone. You follow? I dot one, I dot two, then this is cone. Then I dot one minus I dot two is also cone. Then I dot two minus I dot one is a cone. And minus I dot two, so these are the four cones. And if Q belongs to any one of the cones, then you have a solution. Right? So these cones are called complementary. And if it is a P matrix, then none of the cones. So can you see that? What are the properties of this cone? None of the cones are overlapped. So if Q anywhere this Q is there, right there, anywhere it is there. So you will have a solution and it will have the. But look at this cone. This cones, no, that either one and these two cones are overlapped. Either two minus m dot one and either one, either two is overlapped. So if something is here, Q is here, you will have two solutions. If something is here, you will have two solutions here, and if Q is here, there will not be any solution. So this represents, that any linear system, that IW minus NJ, this kind of linear system is formed, and in order to take care of that conditions, so you can start these two complementary cones, and then you can come out with the solution. Okay. And so there are different kind of cones are possible, and this complementary cones, idea of complementary cones is given by Murthy, and for a given matrix M and alpha, subset of 1 to n, then you can define same alpha, that complementary matrix with respect to alpha. That ith column of complementary matrix with respect to alpha is minus m dot I if I belongs to alpha, and if I doesn't belongs to alpha, it is identical. So both will not offer simultaneously in order to satisfy the complementary condition, and such this will be basis. Okay. And if you collect all of you such that the solution will be not equal to it will not equal, which is called Kn, and theoretically given a vector Q, you have to decide whether S is Q has a solution. So it is enough to check whether Q belongs to a complementary polynomial. So I introduce Q and Q naught matrix, and you will see later on that we will prove that PSD matrix, PSD or PD matrix. So these are basically Q naught, Q or Q naught. PD matrix is a Q matrix, and PSD matrix is a Q naught matrix. So in other words, these are used as a tool to get certain properties of the matrix. These are used as a tool, and that those tools are come from the application. So these perhaps you will not find in this Horn Johnson book or Norman Clemens. Norman Clemens book you will get. That as I told the last chapter. But Horn and Johnson, the topics in matrix analysis, these tools you will not get. So apart from that, tools from either that these are the indirect ways of proving many results in matrix. Session is up to 1 o'clock or 1 o'clock. So I don't have any new slides. So now, if you have any questions, I will be glad to answer. So in this session, what I have got. So I told you what is PSD matrix, PD matrix, and the generalization of PSD and PD matrix. And I have given something for your discussion, the afternoon session, and then I talked about what is co-positive matrix. Okay, so I am giving a talk on 3 decades. I am on 75 years. Okay, I cannot talk about. I started my career even at the age of 25. So I cannot write for 75 years what is the development of the co-positivity. So whatever work you have done on co-positivity, so that is summarized in my talk. 3 decades of you work on 3 decades of co-positivity. You will find. I don't know whether everyone is attending this conference. So that is there is a work on 3 decades of co-positivity. I will be talking about that. What are the open problems are there for co-positive matrices? What are the special class that has been involved co-positive matrices? But here I gave just a small introduction. But there I will be talking in details about the co-positive matrices. Okay. So in 3 decades of co-positivity, I will be talking about. And then I told that there are various matrices involved, which are generalization of. I have told also that PD and PSD matrices, what are the applications? Right? And then what I talked about that what are the generalization of PD and P matrices? So PSD is one of the one that one of the matrices which has been involved, and this has applications in optimization. For PD matrices, you can see our paper. In linear algebra, later on I will group it and give some of the paper. Or those who have that subscription of linear algebra, you can get it from there also. And then I talked about what are there are various subclasses which have been involved for P-naught matrix. So I talked about one of those subclass, so that is called sufficient matrix. And I talked about the application of sufficient matrix. Okay, and then I talked about that many of the matrix classes which have been involved, even for the co-positive matrices, you will see that there are papers that where that it has come the application in gap theoretical application. There, of course, that those are again that the entities are -1, 0, and 1. So it's not very general, but there are lots of results. We could prove on co-positive matrices using using gap theory. And Apart from that, it is heavily used in modern computations that these special matrices are used. Also in interior point algorithms and so this introductory lecture will get into more special matrices. Okay, so so next class is my next class will be. Then after that, the day after tomorrow. Tomorrow one to three. So in the last class, I will be talking about that how to characterize special matrices using DT. Okay, so that will be the content and as I said that there are more than 50 matrix classes, so we can cover only. Yes, Iclaa is there is a workshop group in WhatsApp. There's a Google workshop. If you're not having this free class on Monday, if you need anything, please reply. Why do you? So this situation. Only there after that, here. No, doesn't matter. Perhaps if it works, will not. But it is still. Does this will have a unique law? Does this be? So, I saw this in my stop. Okay, after, okay, now. That he has wrong in that that since the game, the sample is not now in the condition. It's still active. I mean, you have to go on the but there is some which are some two, which not so now. But I'm going to come back. So giving this time, you can store that platform is there, there is no there is no, or there is service there, or there So we go back to install again. Number of telling. Actually.
Neither of those countries.
Copy actually, copy actually, huh?